Bismillahirrahmanirrahim. I'm Hussnain Ali from Bagh School, Murid ke, grade 13 A levels chemistry teacher. This is a question from mock 2 examination paper 4. Here we would be discussing the question. The third question was A part. Complete the electronic structure for iron 0 and iron 3 positive ions. Here the examiner was asking about the electronic configuration of iron 0 and iron 3 positive ions. So I have given you the notes. You can see that the electronic configuration of iron 0 is 4s2 3d6 because while filling the electrons, the 4s is to be filled first, and after that the 3d is filled. As the iron has atomic number of 26, you can go through the notes and see how the electronic configuration is done. While for the ejection of electron to get the iron 3 positive ion, the 4s2 electrons are first ejected, and then further one electron is ejected from the 3d to get the electronic configuration of 3d5 in the case of iron 3 positive. The answers are at the bottom of the slide. You can see them. In the B part of the question number 3 was asking, in an isolated atom, the 5d orbitals have the same energy. When a transition element ion is in an octahedral complex, the d orbitals are split into two groups. B part 1, he was asking, draw an orbital energy diagram to show this, indicating the number of orbitals in each group. So the diagram to be filled has an answer related to the d orbital splitting. As we know that the d orbitals are degenerate orbitals, they have equivalent energy. So when the complex is formed by the linkages with the ligands, they are split into two groups. That in the case of octahedral complexes, that is EG and T2G group. The EG group is basically dz square and dx square minus y square set of d orbitals, while the T2G group at lower energy is dxy, dyz, and dzx orbitals. So the five d orbitals are split into two groups. Two are at higher energy level, while the three are at lower energy level. So by drawing this diagram, you are able to attain 2 marks. In the second part of B, he was asking, use your diagram in one to explain why transition element complexes are often colored. So this was a question related to the color of the complexes. So when the complex, that is octahedral complex here, is formed, the d orbitals are splitted due to the ligands attached and the oxidation state of the central metal ion. So what happens that is when white light falls on it, white light has different energy photons. So amongst those photons, some photons having equivalent energy to the splitting energy. Here the splitting energy is shown by a smaller arrow on the right side. So those photons having equivalent energy to the splitting energy are absorbed, and the electrons that are in T2G level are promoted to higher EG level. This is the factor that gives the color to the complex, because the absorbed photons are not present within the transmitted light, and you are able to see the transmitted light and see the color of the complex. So the three statements were to be given. Here are the three statements. I have given the answer at the bottom of the slide. The first one was that color due to the absorption of visible light. Then the second one was E is equal to HF, or photons energy should be equivalent to E. Here the E is basically representing the splitting energy of the d orbitals. When the photons energy is absorbed, basically what happens is this, that electrons are promoted from lower T2G orbitals to higher EG orbitals. So these three statements would be giving you 3 marks. Be specific about them. I've given you the notes about this type of question, so go through them also. In the third part, he was asking, use your diagram in one to explain why the color of a complex of a given transition element often changes when the ligands around it are changed. So this is a specific question about the ligand field effect on the transition metal complex. Basically what happens, there are two types of ligands. This whole thing is written within your notes, the spectrochemical series, in which we have gone through the strong field ligands and the weak field ligands. So the strong field ligands split the d orbitals to more extent, While the weak field ligands spread the orbitals to a lesser extent, the splitting energy difference is present. Example of strong field ligand is cyanidine, carbon monoxide, and of weak field ligands, iodine, bromidine. You can go through the spectrochemical series. So the strong field ligands would split the d orbitals, and the splitting energy would be having a higher magnitude, while the weak field ligands will split the d orbitals to a lower energy in a lower energy manner. So the splitting energy would be having a lower magnitude. So the size of splitting energy depends on the ligand. So what happens that due to this the coming ligand, the splitting energy changes, and thus the absorbed photon that is absorbed due to the splitting energy difference for the promotion of electrons from lower energy level to higher energy level is changed. So the color of the complexes gets changed. So the answers are given. You can see the answers, and after that, we will be coming to the C part of the question number 3. He's saying that heating a solution containing potassium ethane dioate, iron 2 ethane dioate, and hydrogen peroxide, it produces the light green complex of potassium iron oxalate, which contains an ion potassium iron oxalate 3 negative. The structure of ethane dioate ion is as follows. Calculate the oxidation number of carbon here. If you want to calculate the oxidation number of carbon, the easiest way was that you should have done the from the you should have taken the C2O4 2 negative ion situation here, because in the case of C2O4 2 negative ion, there would be a net 8 negative charge on oxygen atoms, while 6 positive charge on the carbon atoms, so as to give the whole oxalate ion or ethane dioate ion a 2 negative charge. So on the carbon, the oxidation state was 3 positive. Students have mistakenly written 4 positive, so avoid this mistake any further. In the second part, he was asking the calculate the oxidation number of iron in iron oxalate complex having a 3 negative charge overall. So an oxalate ion or ethane dioate ion, uh, it has a 2 negative charge. So in the second part, the oxalate ion or ethane dioate ion has overall 6 negative charge, while the iron should have a 3 positive charge, so as to make the whole complex 3 negative. So the oxidation state of iron here should be 3 positive. In the third part of the C, the examiner was asking the iron atom in the iron ethane dioate ion is surrounded octahedrally by 6 oxygen atoms. The ion shows stereoisomerism. Complete the two diagrams of the ion showing both stereoisomers. So stereoisomers case was asked here. Here the basically octahedral complexes are forming the stereoisomers that are basically optical isomers. You can go through the notes and see why this will form an optical isomers. The answer is shown here. As you can see in the above diagram, the oxalate ions are attached with the central metal ion with the help of oxygen linkages. So this diagram matters a lot. In the second diagram, the second stereoisomer or the optical isomer of the first one is drawn. Basically, this is showing an inversion, right to left inversion or left to right inversion. So these are the two optical isomers which were to be drawn, and you were able to get the relevant marks from this part also. Uh, in fourth part, in sunlight, the complex decomposes in potassium into potassium ethane diode, iron 2 ethane diode, and carbon dioxide. The balance the equation for the decomposition. This was a question related to the balancing of equation. This was a simple question. All you have to do is balance the potassium first. If you will be balancing the potassium first, you would have to write 3 on the right side while 2 on the left side. So potassium becomes 6 on the both sides. While for the iron case, as iron gets disbalanced, it 2 is to be written on the iron oxalate side, that is your right side, and further 2 is to be written with the carbon dioxide so as to balance the whole equation. The answer of this whole balancing is written at the bottom of the slide. Hopefully you are able to understand all of the concepts related to transition metal ion complexes here. Go through the notes also and take care. Allah Hafiz.